Welcome to JB's Academy of Science. In this lesson, we are going to learn about Gauss's theorem, applications of Gauss's theorem, and problems using Gauss's theorem. Gauss's theorem. Gauss's theorem deals with the electric flux passing through a closed surface. It states that the total electric flux through a closed surface is equal to 1 by epsilon 0 times the total charge enclosed by the surface. If we have a closed surface and there is some charge placed within that closed surface, then the electric flux passing through the entire surface due to the charge present inside is equal to phi is equal to Q by epsilon 0. Flux is equal to 1 by epsilon 0 times the charge inside the surface. So this is Gauss theorem. Gauss theorem verification. We can verify Gauss theorem by considering an example. Let us consider a charge plus Q. Consider a closed surface around the charge plus Q. If you consider a closed surface to apply Gauss theorem, such a surface is called a Gaussian surface. So here, for simplicity, let us consider a spherical surface of radius r. Let P be a point on the surface of the sphere. The electric field due to the charge at P is shown in the direction. And consider a small area ds around the point P. The direction of the area element is also shown in the figure. Now, the electric field at P due to the charge Q, E is equal to 1 by 4 pi epsilon 0 Q by R square into R cap. The flux passing through the small area ds, d phi is equal to E vector dot ds vector is equal to E ds cos 0 is equal to E ds. Electric field and area element both are in the same direction. The angle between them is 0. So cos theta becomes cos 0. Now, the total electric flux passing through the entire sphere, phi is equal to integral d phi is equal to integral EDS, that is integral 1 by 4 pi epsilon 0 Q by R square ds. That is phi is equal to 1 by 4 pi epsilon 0 Q by R square integral ds. If a small area is integrated for a sphere, the whole surface area is 4 by R square, where R is the radius of the sphere. So phi is equal to 1 by 4 pi epsilon 0 Q by R square into 4 pi R square. That is phi is equal to Q divided by epsilon 0. Thus, Gauss theorem is verified. Now let us look at some applications of Gauss's theorem. Electric field due to a line charge distribution. Consider a linear charge distribution of positive charges as shown in the figure. We have to find out the electric field due to this charge distribution at a point near to the distribution. So consider a point P which is at a distance small r from the charge distribution. Now, to apply Gauss theorem, we have to construct a Gaussian surface, a closed surface around the charge. Let us consider a small length L on the charge distribution and imagine a cylinder around the charge distribution whose length is L. Now this cylinder has three surfaces, two bases and one curved surface, one lateral surface. Now let phi1 be the flux passing through the curved surface, phi2 flux through base 1 and phi3 flux through base 2. The net flux phi is equal to phi1 plus phi2 plus phi3. Now in case of the two base areas, the area element and the electric field are perpendicular to each other. E and ds2 are perpendicular. E and ds3 are perpendicular. Therefore, the flux passing through two bases will be 0. That is phi2 is equal to phi3 is equal to 0. Therefore, the net electric flux through the cylinder is phi is equal to integral E dot ds1. That is E dot 2 pi RL, where 2 pi RL is the lateral surface area of the cylinder. Now, let lambda be the linear charge density of the distribution. Now, charge on L length of the distribution Q is equal to lambda L. Applying Gauss theorem, the electric flux is 1 by epsilon 0 times the charge. So E into 2 pi RL is equal to lambda L by epsilon 0. Therefore, E is equal to lambda by 2 pi epsilon 0 R. In vector notation, E vector is equal to lambda by 2 pi epsilon 0 R n cap. N cap gives the direction of the electric field. Now, electric field at a point near to a plane sheet of charge. So consider a plane sheet which is charged positively or negatively. Now consider a point P near to the charge distribution. We have to find out electric field at P due to the plane sheet of charge. Now we can find the electric field by applying Gauss theorem. To apply Gauss theorem, we need a closed surface which is called a Gaussian surface. Now consider a cylinder towards either sides of this charge distribution. Half of the cylinder is towards right and half of the cylinder is left. Now the point P is on the base of the cylinder. Now let sigma be the charge density of the charge distribution. Let A be the area of the base of the cylinder. Then the charge enclosed within the Gaussian surface is equal to Q is equal to sigma A. Now there will be an electric field at P and whose direction is shown here. Let us consider that direction is along the x direction. The net electric flux through the entire cylinder is equal to the flux through two base surface areas. Electric field is perpendicular to the area vector on the curved surface. Therefore, electric flux through the curved area, the lateral surface area will be 0. Therefore, the entire electric flux is due to electric flux through two base areas of the cylinder. That is phi is equal to EA plus EA, that is equal to 2EA. Applying Gauss theorem, the net flux is 1 by epsilon 0 times the charge. That is phi is equal to sigma A divided by epsilon 0. That is 2A is equal to sigma A divided by epsilon 0. Or electric field E is equal to sigma by 2 epsilon 0. So that is the electric field at a point near to the charge distribution. Electric field due to a charged spherical shell. Now consider a spherical shell of radius capital R, which is charged. Now we have to find out the electric field due to this charged spherical shell at a point outside the shell and at a point inside the shell. Let sigma be the surface charge density of the charge distribution on the shell. Now, charge on the shell Q is equal to sigma into 4 pi r square. Now, case 1, electric field at a point outside the shell. Consider a point P at a distance small r from the center of the shell. Consider a closed surface which is called Gaussian surface. For our convenience, let us consider a sphere of radius small r around the spherical shell. Consider a small area ds, area element. The direction of the electric field and the area element are shown in the figure. Both are outwards, radially outwards. Now, electric field is radially outwards. Area element ds is also outwards. They are the same directions. The angle between them is 0. The entire electric flux passing through the spherical shell, the Gaussian surface, phi is equal to integral E dot ds is equal to E dot 4 pi r square. Applying Gauss theorem, phi is equal to Q by epsilon 0, that is 1 by epsilon 0 into sigma 4 pi r square. That is E into 4 pi r square is equal to 1 by epsilon 0 into sigma 4 pi r square. That is E is equal to 1 by 4 pi epsilon 0 Q by r square, or E is equal to sigma by epsilon 0 into r square by small r square. Now, electric field at a point inside the shell. So consider the point inside the shell. Consider the Gaussian surface of radius r prime. Now, the electric flux phi is equal to integral E dot ds, that is E dot 4 pi prime square, 4 pi r prime square. Applying Gauss theorem, phi is equal to Q by epsilon 0, that is 0, because charge enclosed within the Gaussian surface is 0. Since all the charge is outside, charge enclosed by the surface is 0. Therefore, E dot 4 pi r prime square is equal to 0. So, electric field inside the spherical shell will always be 0. Now, let us do some problems based on Gauss's theorem. A charge of 8.85 picocoulomb is placed at the center of a non-conducting spherical shell of radius 2 meters. What is the electric flux passing through the sphere? Charge Q is equal to 8.85 into 10 to the power of minus 12 coulomb. Radius of the sphere R is equal to 2 meters. Electric flux phi is equal to integral E dot ds, that is equal to E dot 4 pi R square is equal to Q by epsilon 0. Q is 8.85 to 10 to the power of minus 12. Epsilon 0 is also 8.85 to 10 to the power of minus 12. Both will get cancelled, is equal to 1 Newton meter square per coulomb. That is electric flux passing through the sphere. A charge of 10 microcoulomb is placed at the center of a cube of sides 10 centimeter. What is the electric flux through any one face of the cube? The whole electric flux passing through the cube phi is equal to integral E dot ds, that is equal to Q by epsilon 0. Therefore, flux passing through any one face of the cube is 1/6 of the total flux passing through the entire cube. That is 5 by 6 is equal to 10 into 10 to the power of minus 6 divided by 6 into 8.85 into 10 to the power of minus 12. That is 1.88 into 10 to the power of 5 Newton meter square per coulomb. Thanks for watching the video. Please write your feedback and suggestions in the comment section. We'll be coming up with another video in the coming weeks. Thank you.